Well, the problems we're working on today may very well be the most difficult problems in the entire course for the whole year. So if you can get through this section, you will be in fantastic shape because hardly anything else that we do is going to tax your brain as much as this will. So again, if you can get through this, there'll be a lot of other concepts that we're going to talk about, some other math that we're going to be doing. But this module, and particularly surfaces that are sitting on an inclined plane, tend to be the ones that are the most difficult for students. So if you struggle with this, don't be surprised, but I have confidence in you and I think you can do this. All right, so a lot of the Newton's second law problems that we have been doing so far, in fact, all of them that we've been doing so far, have involved the object sitting on a horizontal surface. And we've talked about a force pulling one direction, friction going the other direction, normal force going up, weight going down. So if I have an object on an inclined plane or on a ramp of some sort, on a slope of some sort, the same forces are still there, but mathematically I have to look at them differently because now I no longer have motion in a horizontal direction. Now it's at an angle. And so if I look at this just from, just in very generic terms, the first thing that I have to look at is, okay, the weight of this object is going to act straight down because that's what weights do. That's the way gravity is pulling. However, the object is sliding this direction. It's not horizontal and it's not vertical. So having a weight acting at this kind of angle is not going to help me at all. Additionally, the normal force, and I just realized I have a very crooked box there, the normal force always acts perpendicular to the surface of whatever this object is sitting on. So the normal force, if the surface is going this way, the normal force is going to act in this direction. So in order to be useful, in place of having just the weight, I need to have the force that's acting in the same dimension as the normal force, and so that's going to be the one that's going this direction. And he didn't go through all of the geometry in order to get here, and you don't need to know all the geometry, you just need to know how to work the problems for right now. Okay, so this is going to be equivalent to W times the cosine of theta. And theta is the angle that your slope is at, or that your incline is at. So this is the theta, whatever this angle is, and you're going to take the weight of the object times the cosine of theta to get the force in this direction. Keep in mind that that's going to be equivalent to the normal force because the object's not moving in this direction, and so therefore the sum of the forces has to be equal to 0. Now, if you have an object sitting on a slope that's this way, obviously the weight of the object is going to be pulling it downward. So here, this is the component of the weight that's actually accelerating the object downward. And so this is going to be the weight times the sine of theta. And assuming that I do not have a frictionless surface, friction always acts in the direction opposed to the motion. So it's going to be acting in that direction. Now, how can I relate these four forces to each other? Well, I already told you that the normal force is going to be equivalent to the weight times the cosine of theta. So I know that relationship. Okay. I also know that the frictional force is equal to the coefficient of friction times the normal force. Okay, we had that from a couple modules ago, so that should be something that's familiar to you. Now, we know from Newton's second law that the sum of the forces is going to be equal to the mass times the acceleration. Well, if I look in the dimension of the motion, this is going to be the direction where the motion is. So what that means is that if I take the weight times the sine of theta. If it's moving this direction, I know that this force is going to be greater than this one. So if I take this force and subtract off the frictional force, that's going to give me the acceleration, the mass times the acceleration of the object, okay? So that's where this comes from. This is what's pulling the object down. The friction is holding it back, and then the sum of these two forces is going to be equal to the mass times the acceleration. Now I said sum, so basically what I'm doing is I'm defining the direction down the slope as positive and the direction up the slope as negative. But if you just think about, you're going to subtract off the friction from the downward force, that will give you the mass times the acceleration. So these are the three relationships that you're going to need for any type of inclined plane problem like this one. And these four forces are going to be pretty standard in any problem that you're working. So let's look at example 6.5. In example 6.5, he says a 35 Newton block slides down a board that is inclined at 30 degrees. If the coefficient of kinetic friction between the block and the board is 0.12, what is the block's acceleration? Okay, so let's get this information in here. So first of all, I know that the weight is 35 newtons, okay? I was told that theta is 30 degrees, so I can actually go over here and put this 30 degrees in. Theta equals 30 degrees. I was told that the coefficient of kinetic friction is 0.12, and I am asked what the block's acceleration is, okay? So, what information do I have? Where am I going to have to start with this? In order to be able to find out what the acceleration is, I'm going to have to know what the mass is, for starters. I'm going to have to know the frictional force. To know the frictional force, I'm going to have to know the normal force, okay? So I'm going to have to use all of these relationships in order to figure all of this out. So where we will start then is we'll say, I know the weight already, and so I know that the normal force is equal to the weight times the cosine of theta. I know the weight, it's 35 newtons, and I know theta, so the cosine of 30 degrees is what's going to go in here. So that tells me that when I do that math there, my normal force is going to be 3.0 times 10 to the first newtons, okay? So now I have the normal force. Knowing the normal force, now I can go in and figure out what the frictional force is going to be. So the frictional force is the coefficient of friction times the normal force, so that's 0.12 times the normal force I just calculated, 3.0 times 10 to the first newtons. And then when you plug that math into your calculator, you come up with 3.6 newtons to two significant figures. Okay, so I know the normal force, I now know the frictional force. Now I should be able to find what the acceleration is now that I know these other things. So now I'm going to use this W times the sine of theta minus the frictional force equals the mass times the acceleration. Okay, so the weight is 35 newtons times the sine of 30 degrees minus the frictional force that I just calculated is 3.6 newtons. Now what about the mass? I don't have the mass, do I? Well, if I have the weight, I should be able to calculate the mass pretty easily because we know that weight equals mass times gravity. So if this equals mass times gravity, and you know that gravity is 9.8 meters per second squared, you're going to take 35 newtons divided by 9.8 meters per second squared in order to come up with the mass. We've done a lot of those problems, so that shouldn't be difficult for you. The mass comes out to be 3.6 kilograms, and then I'm going to have to solve for A. So multiply this, subtract this, divide by 3.6. Again, we're down to just algebra at this point. And so then your acceleration is going to come out to be 3.9 meters per second squared. Okay? So basically, if you're going to be working one of these inclined plane problems, you need to keep in mind these three relationships. Depending on what they've given you, you're going to just be manipulating these relationships until you can figure out the variable that they're asking you for. But these three relationships will always hold. This diagram is pretty well always going to be the case. Sometimes you will get lucky and they will tell you, oh, assume that it's frictionless, assume that you don't have any friction. So that really makes the problem nice if you can assume that there's not any friction. Because at that point, if there's no friction, then W times the sine of theta is equal to the mass times acceleration. You can just leave that part out because there isn't any friction. Most of the time, though, there is going to be, and so you're going to have to include that piece in there. Again, it's really, it's a matter of figuring out what you know, what you need to find, and figuring out how to manipulate the information you have in these three relationships to come out with the answer that you need. Okay, so be patient with yourself. Again, make sure that thinking cap's pulled down tight and snugged on real good, and I think you'll be able to handle these.